So I'm going to talk about computer vision. And computer vision is a branch of artificial intelligence, and it deals with the automatic analysis of images and video by computers. It has a lot of applications: medical diagnosis, biometrics, self-driving cars, future cities, and all kinds of things. So I'm with Center for Research in Computer Vision, CRCV. Beside myself, we have three other faculty, Dr. Yogesh Rawat, Dr. Abjit Malanabas, and Dr. Chen Chen. Abjit and Yogesh have already presented in the seminar, and hopefully Chen Chen will present in fall. So beside that, it's a very small center because we have only 4 faculty, but we have several associate faculty from different departments at UCF and our collaborators from different countries. And we have 3 postdocs, and then we have a large number of Ph.D. students, about 30 of those, and those are the ones who do most of the work. These are the highlights of our center. We are bringing a lot of money, and we have won awards, and then the highlight of our accomplishment is we had 6 CVPR papers. Now, CVPR is a major conference computer vision, and it is ranked number 5 in all sciences by Google. So you see the Nature, New England Journal of Medicine, Lancet, and Science, and the CVPR, so which we are very proud of. It's being a conference, it has such an impact, and we had 6 papers from here this year. So we are very happy about that. So I'm going to talk about the projects which are currently funded. I'm the PI, very quickly to give you a flavor. So this is a project from IARPA. IARPA is like Intelligence DARPA, and this is the 4-year project, and we are phase 3, and it's going to end this December, and deals with recognizing activities in video. And these are the activities where there are cars, there are people, and we want to look at what is happening in the video. And we have total 37 activities, and it's a very complex problem. You have to detect, track, and distinguish between different activities. And this is evaluated by NIST on a sequestered data set, so which we don't have any access. And as you see, we did very well. We came on the top of leaderboard. This is the real time, is number one here, is the real time. We are faster than real time, 3 times faster than real time. And this is the performance metric. The lower the better. We are here, we are better than the IBM, CMU, and Purdue, and so on. So which we were happy about that. This is a project which is funded by Army Research Office and deals with the grounding. So the problem is a visual question answering. Given this image like that, the question is, are the black horses to the right of the vehicle on the road? Okay, so typically we will get yes or no. It's a question answering. But what we want to do, we want to ground it, and we want to say, how did system come up with the answer? And we came up with localization of these the horses and the vehicle, that it used this information to give that answer. There's another example. There's a cube that is in front of the blue rubber cylinder. It is the same color as a metal sphere, and it says false, no, and because of this grounding, that the same color is not same. So this is a project funded by National Geospatial Intelligence Agency, and here the idea is to geo-localize. We are given an image, it's a ground image, and we want to find out GPS location of that. And the reference images are the satellite imagery, so which are shown here. And this was the first image, and we can geolocalize with 0 meter. So another example, here we can geolocalize within 2 meters. And so on, many good examples, cross-view geolocalization. This is a DARPA project. It deals with the adversarial attacks, the DARPA TMVT. And as you know, the deep learning works very well. So suppose, it can recognize this is a panda by close to 60% accuracy. But the problem is if you add small perturbations, small noise here, and then to this one, it will say it's a given, completely different with 93% confidence. So this is called adversarial attack. So in this project, we are working on the pure black box attacks. So one is the white box attack, where we have access to the where we want to attack, but black box, we don't know anything about the classifier which we want to attack. So we start with a noise, we come up with a perturbation, and then we train the substitute classifier, which are like a surrogate classifier of the target classifier, which we don't know, and we add that perturbation, and we can do the attack, and we can do actually up to 60%. The accuracy drops to 60%, which is very nice. Now the previous one was that we want to do attack. Now this second DARPA project is a reverse engineering, that we want to actually reverse engineer the attack. So here we want to detect that there was an attack, and we want to extract the signature of the attack, and we want to identify which family of this tool chain was attacked, because there are different kinds of attacks, and then we want to come up with a clean sample. So in this approach, we start with the clean image, we add a perturbation, and we get this adversarial image, and we come up with the denoise image, the clean image, and we subtract that from the adversarial image, we get the signature, and we classify that. So we are doing pretty well in this. So if we use on a adversarial images, we do about 50%, but if we do on the perturbation, we can do 77%. So we just finished phase 1, so we are going to go to phase 2. So the third DARPA project we have, which is very interesting, is on the semantic graphs or the schema. So the idea here is that we want to come up with, use these, the do-it-yourself videos, like this is the hedge or hog plus, how you make this kind of thing. And we have a bunch of videos, and we want to take these videos, come up with this semantic graph that how this particular do-it-yourself task work, and come up with a summary of that. So then the final project we have, it's funded by Lockheed Martin, and we want to do tracking here. So this is the sequence, RGB sequence, and we want to detect people, and we want to track it, and we want to do this continuously, and we don't have to have ID switches. And here we can apply the same method for the LiDAR data, which we have the 3D data, point clouds, and we can put these actually 3D bounding boxes in X, Y, Z. And these kind of things applicable in self-driving cars, because lots of self-driving cars need to detect people or vehicles and track them to avoid the accidents. So before I end, I want to quickly talk about some of the education and training related projects we have. So this is a project funded by National Science Foundation, and this is a site for the research experience for undergraduates. Now, RU supplement, you can get 1 or 2 RU students on each NSF grant, but this is the whole site where we have 10 undergraduate students spend 10 weeks with us at summer. And we have been doing this for a long time, this is the 34th year, and we have about 340 students have participated from 75 different countries all over 75 different schools all over the country. And this year we have these students, actually we are ending this project next Friday, and we will have a poster session. Then we have another NSF project, $1 million grant from National Science Foundation under the A-System project. And this is for the transfer students. So the transfer students from 2-year community college, when they transfer to university big like UCF, they get lost because of large university, different culture, and high expectation, high standards. And they come in as a system major, but then quickly they drop out. So the idea here is that we want to select those students who are financially challenged and also academically talented and mentor them so that they can stay in the system major. And we are in the 4th year of this project, and we will have 1 more year to go. So finally, this fall, we are starting a Master of Science in Computer Vision. And this is the first time any public university in US is offering this program. So we are very excited for that. Thank you.